This trajectory has remained unexplained for over 85 years. It appears chaotic, bouncing violently across the number line with no discernible limit. The path is generated by the Collatz conjecture. If a number is even, divide it by 2. If it is odd, multiply by 3 and add 1. These hailstone sequences behave like this diagram. Large integers spike into extreme values before suddenly crashing down to 1. On a linear number line, these jumps look like random noise. We have tested trillions of integers, and every single one eventually returns to 1. However, no formal proof exists to explain why this happens for every possible starting number. The difficulty may stem from how we view the problem. Since the 1930s, mathematicians have studied the sequence almost exclusively as a one-dimensional system of moving points. This linear perspective hides the underlying structure. It forces us to see complexity where there may actually be a rigid geometric order. Researcher Sebastian Schoepis suggests that the 3n+1 map is not the core of the problem. He argues that the math we've been using is just a simplified version of a more complex reality. This visual represents the shift in perspective. The erratic linear plot is actually a flattened view of a two-dimensional orbital system. In this polar phase space, the jagged spikes align into smooth, concentric pathways. The erratic behavior starts to follow a visible, curved geometry. By treating the sequence as motion through a coordinate system rather than jumps on a line, we can examine the specific rules that drive every number toward the center. To map this space, we begin with a two-dimensional polar plane. The number 1 sits at the center, serving as the origin for all movement. We then apply a new metric to every integer, a 5-layer resonance score. This score maps a number's reaction to 2 and 3. It establishes the radial coordinate, generating 5 distinct concentric orbital shells. Every positive integer has a fixed home shell here. Its angular position then changes based on its mathematical history. Instead of points on an infinite line, we now see integers as bodies locked into a specific orbital phase space. We can now reinterpret the Collatz operations as physical movements within these orbits. Consider a single number starting on an outer shell. When divided by 2, it doesn't just get smaller on a line. In polar space, division by 2 is an angular rotation along the circumference of its current shell. The 3n+1 step is similarly transformed. This operation corresponds to a radial transition. It shifts the number from its current shell directly to a neighboring shell closer to the origin. What looked like erratic spikes on a number line is actually a coordinated sequence of smooth rotations and inward steps toward the center. The complexity of the Collatz sequence is a side effect of projecting this two-dimensional motion back onto a flat number line. This orbital framework also reveals why different types of numbers follow different patterns, specifically primes. Because prime numbers lack internal factors, their resonance scores align cleanly with the shells. They avoid the erratic jumping behavior seen in composite numbers. As shown here, primes often remain locked on a single shell for long periods. They rotate smoothly before eventually making a clean radial transition inward. Composite numbers behave differently because they contain multiple internal factors. These numbers experience more frequent radial transitions, zigzagging between shells rather than maintaining a stable orbit. While individual paths vary, the overall geometry of these transitions follows a single rule. The space is contractive. The vector field of the space shows that every radial transition has a net inward bias. The arrows point consistently toward the origin. There are no stable orbits in the outer shells that allow a number to stay there forever. This contractive bias ensures that no matter how a number rotates, it is eventually pulled toward the inescapable center. We can see this in action by observing thousands of integers. These nodes represent a massive range of starting values. When we run the sequence, the entire system flows inward. Numbers rotate and drop, shell by shell, draining toward the central point. This polar model provides a physical context for the operations we've been studying for 80 years. A number's magnitude is its distance from the center, and its sequence of operations is the path it takes through the orbital shells. Because the radial bias is always inward, and there are no stable outer loops, every path must converge. The number 1 acts as a mathematical attractor. It is the only terminal point in the entire system. Every integer, regardless of its starting size, is caught in this inward flow. The collapse to 1 is a requirement of the geometry. The return to the center is inevitable